Hello! In this video I will show you what exactly derivation means. By definition, derivation is a basic mathematical operation that can be performed on a function. It can be defined with the help of limit value calculation, but in reality, the derivation is so basic and practical concept that people can understand it intuitively without any mathematical background. I will first explain the idea of derivation with the help of some animations and examples. Once you have the basic concept, we formalize it mathematically. To understand this video, you need to understand only some simple functions. First things first, you can see the control panel and sensor output of a robot. This robot, symbolized by the red circle, is simple but obedient. We can send it anywhere on a straight line, and it does its best to reach the selected point as fast as it can. The robot has three independent onboard sensors. The first sensor measures its distance from the starting point, so it measures the location. The second sensor measures the speed, like the sensor you have in your car or on your bicycle. The third sensor is an accelerometer, which you probably have in your smartphone. These values are natural and sensible for us. We can determine our position, we can feel the speed, and we can sense the acceleration. Let's send the robot to somewhere and analyze its sensors. The movement can be divided into three sections. In the first section, the robot starts its long journey. It engages its thrusters and measures constant acceleration. The speed and distance increase. In the second section, the robot just drifts. It only burns fuel to overcome friction and air resistance. The acceleration is zero here, the distance from origin is still increasing. When the robot reaches its destination, it must brake, suddenly. Braking suddenly reduces the speed to zero, acceleration has a negative value, and the increase in distance stops. As I told you, these three sensors are independent, but still their values look like they have some connection. Well, this is true. When we derivate the position according to time, we get the speed. When we derivate the speed, we get the acceleration. These are true by definition. From this picture, we can get some instinctive understanding of the derivation. Derivation is change. If the derivative of something is zero, it does not change. That's why we got constant speed in the second section while the acceleration was zero, and that's why we got constant position while the speed was zero. Now all we have to do is define the change. We can steal some idea from traffic code where the steepness of a slope is defined by the ratio of the vertical rise to the horizontal distance traveled, like you can see in this example. Here, while the car travels 10 meters horizontally, it elevates 5 meters vertically. The ratio between the two is 0.5 or 50%, but in mathematics we prefer to use the ratio over percentage. The ratio could be a good definition for derivation, but how can we apply it when the function is not straight but curved, like in the next example? In this case, we can't really define a globally true ratio, but good news, if we zoom enough, every curve is straight. Here we can define the ratio as we did in the previous case. Of course, this ratio changes if we zoom to another point. It depends on the x. Now you have an intuitive understanding of derivation, but we still didn't use any formalization or calculate anything. We will change that. Let's start with a straight function where we don't have to zoom. To calculate the derivative, that is the vertical to horizontal ratio, we must first decide what the vertical distance should be. It could be anything in this case, so let's pick the 2. After that, we have to calculate the belonging vertical distance, which is 6. Now we see that the derivative of this function is 3. We can calculate this directly from the function. We just have to divide the change of the function by the change of x. The derivative of this linear function is a constant. It's not depending on the exact value of x. It changes in the same way everywhere. I would like to refer back to the robot scene at the beginning of this video, where the speed increased linearly, the acceleration had a constant value. But what should we do when the function is not linear and its steepness depends on the value of x? In this case, we have to select a very small horizontal distance. Let's call this distance epsilon. Epsilon is a Greek letter and usually it refers to a very small number. But how small should it be? As I told you, if you zoom enough to a function, it becomes linear. So this epsilon should be so small that every chaotic function becomes linear in its scale. If you want to calculate the derivative of an unknown function using a computer, this is all you have to know. You have an equation with the parameter epsilon, which must be chosen according to the function to be derived. But if you want to get the exact derivative for a function, you have to use limit value calculation. This is easier than it sounds. You just have to assume that epsilon is almost zero, and you have to substitute into the formula and simplify it. Mathematicians have a special symbol for ascensions like this. It's called the limit. Let's do this on fx is equal to x squared. We have to use the previously discussed formula with the limit. This is the same as in the linear case. We calculate the ratio between the horizontal and vertical distance, but we also state that epsilon is very small. It tends to zero. At this step, we can't just substitute it with 0 because that would cause a division by 0. But we can substitute fx and expand the parenthesis. After x squared is disappeared, we can divide by epsilon because all members of the addition are multiplied by it in the numerator. We have done the division by epsilon, now we can substitute the limit. And we are ready. The derivative of x squared is 2x. Using this formula or definition, we can calculate the derivative of any function numerically by a computer or symbolically using pen and paper. And we are finished. We didn't cover some topics like the partial derivative of multidimensional functions or the condition for the existence of the derivative. These are important and interesting topics, but I think this video is pretty dense and intense even without them. I hope you understood everything, but if this is the first time you heard about derivative, I doubt it. This is an easy topic after you understand it, but hard to swallow it at first. For ease of understanding, I prepared a small cheat sheet with some homework. It has 5 sections. The first is just the 3 commonly used notations for derivation. Okay, it contains a little lie. The third one is used for partial derivative. The second section contains 2 possible definitions. The first one was used in this video. The second one is the same, but instead of epsilon tending to 0, we use a different Greek letter called xi that tends to x. They are the same if you replace epsilon by the difference of xi and x. The third one contains some commonly used rules. They can be derived from the definition, and I suggest you to try it. It's a very good practice. The fourth section contains the derivative of some important functions. They can be also derived from the definition, but not all of them are easy to prove. The last section contains some exercises with the solution. I suggest to start with these. Please check the description for the cheat sheet and for some other downloadable content. Thank you for watching. This was my first video and I hope you enjoyed it. If you have any comment or question, please don't keep it to yourself, and if you enjoyed it, press a like and subscribe. My main goal is to delve into the depths of quantum computing with strong theoretical and mathematical background using simulations and exact calculations, so you will find both basic and advanced math videos here with some general IT topics only for relax. Thank you.